You might think of a chemical reaction as a simple hill climb. Molecules gather energy, reach the top of an energy barrier, and slide down into a new product state. That is what classical models like the Arrhenius equation tell us. Reactions happen when particles gain enough heat to overcome this barrier. But here's the strange part. In many cases, reactions happen much faster than the models predict. Sometimes molecules behave as if they have found secret tunnels through the barrier, avoiding the climb altogether. This is the heart of the reaction kinetics anomaly paradox, where reactions seem to cheat the rules we thought we understood. In this video, we explore how certain reactions move faster or take paths that classical theories cannot explain. From hydrogen atoms tunneling through barriers like ghosts, to reactions unfolding in crowded molecular environments where trillions of possible paths compete, we will see why the old hill climb picture no longer fits. Even when every molecule follows time-reversible laws, the combined behavior of many particles, stirred by quantum effects and environmental noise, creates an irreversible flow toward products. This is chemistry's version of organized chaos. And it reveals just how deep the gap is between simple theory and the rich reality of how matter changes.
How do some chemical reactions proceed at rates that defy the predictions made by classical activation energy models, even though the molecular motions underlying them follow time-reversible laws? Chemical reactions are often depicted as a well-ordered march over an energy barrier. According to classical theories, such as the Arrhenius equation and transition state theory, reactants must accumulate enough thermal energy to climb this barrier in order to form products. Classical physics assures us that the microscopic equations of motion, be they Newtonian or quantum, are reversible. In an ideal situation, if every molecular velocity were reversed exactly, the reaction would retrace its steps and return to the original state. Yet, in practice, once a reaction takes hold, the rate at which it proceeds and the pathway it follows often appear to shortcut these predictions in a manner that seems almost paradoxical. So far, so good, until we take a closer look. The reaction kinetics anomaly paradox emerges when the neat symmetry of time-reversible molecular dynamics collides with the overwhelming complexity of reaction pathways and quantum effects. Under ideal conditions, if every atomic vibration and collision were controlled with absolute precision, the formation of a transition state would strictly follow the energy barrier predicted by classical models, and the reaction rate could be determined simply by the thermal energy available. However, in many chemical systems, the pathway to products is not a straightforward climb over a single barrier. Instead, the reaction swiftly finds alternative shortcuts that allow it to proceed at unexpectedly high, or sometimes surprisingly low, rates. One striking example occurs in reactions involving light particles, such as hydrogen atoms or protons. These particles exhibit wave-like properties that allow them to tunnel through energy barriers that, by classical reckoning, should be insurmountable. This quantum tunneling means that even when the overall thermal energy is insufficient for barrier crossing, the reaction may proceed anyway, much like a drop of dye dispersing irreversibly in water, despite the underlying reversibility of individual molecular motions. At even smaller scales, the story grows even more intricate. In systems with countless interacting particles, each with numerous possible energy states, the numbers add up astronomically. What one would expect to be a neat, reversible passage through a single energy threshold turns into a cascade of alternative pathways and transient intermediates, as with the irreversible mixing of two fluids, where the enormous number of microscopic configurations guarantees that the mixed state vastly outnumbers the unmixed. The reaction's progress is biased by statistical probabilities that favor the formation of products. The reversible nature of each individual molecular collision becomes irrelevant when pitted against the overwhelming likelihood that the reaction will find its way to completion. And then there's the matter of environmental influence. In real chemical systems, subtle perturbations, be it from solvent fluctuations, vibrational couplings, or even slight imperfections in the molecular ensemble, prevent the perfect, reversible crossing of the energy barrier that classical models would predict. These fluctuations, much like the tiniest disturbances in a stirred fluid, ensure that any attempt to reverse a reaction, or even to slow it down in line with classical expectations, results instead in an accelerating march toward increased disorder and product formation. Even in meticulously controlled conditions, where chemists design reactions to follow precise pathways, these quantum and dynamic effects impose their own rules. Microfluidic devices or ultra-clean reactors, designed to eliminate all external perturbations, still reveal reaction rates that outpace classical predictions. The seemingly impossible shortcuts taken by the reactants underscore the fact that while microscopic dynamics are reversible in theory, the sheer complexity and statistical nature of real-world molecular interactions lead to an effectively irreversible process, one that the classical activation energy models simply cannot capture. So what's really going on? The paradox does not imply that the fundamental laws of physics are wrong. Rather, it highlights the limitations of applying idealized, time-reversible models to systems where alternative quantum pathways, non-statistical dynamics, and overwhelming statistical probabilities dictate the outcome. The idea of a simple barrier-limited reaction derives from models that assume perfect control over every molecular interaction, neglecting the profound impact of quantum tunneling, transient energy redistributions, and environmental fluctuations. In reality, the collective behavior of countless molecules overwhelmingly favors pathways that bypass the classical energy barrier, resulting in reaction rates that defy our classical intuitions. The reaction kinetics anomaly paradox serves as a vivid reminder that while our microscopic equations of motion are in principle reversible, the complex, high-dimensional dance of molecules leads to a macroscopic reality where reactions flow irreversibly toward products. It challenges us to rethink the relationship between microscopic order and macroscopic chaos, and to embrace a richer, more nuanced understanding of chemical kinetics that accommodates the surprising shortcuts offered by quantum mechanics and statistical dynamics. The reaction kinetics anomaly paradox reveals a perplexing scenario. While classical activation energy models, like the Arrhenius equation and transition state theory, predict a reaction rate based on a well-defined energy barrier, experimental observations show that certain reactions proceed at speeds that significantly diverge from these predictions. Example, in hydrogen transfer reactions, classical models predict a slower conversion rate based on the energy barrier. However, these reactions are observed to occur much faster than anticipated. Analogy. It's akin to having a locked door with a specific key. According to conventional wisdom, you must have the right key to open it. Yet some reactions seem to have a hidden bypass that allows them to slip through the door without using the key in the standard way. Traditional kinetic models are built upon the notion that reactants must acquire sufficient energy to overcome an activation barrier as mathematically described by the Arrhenius equation. In contrast, the anomalous behavior is characterized by reaction rates that defy these predictions, especially under conditions where quantum effects or alternate pathways are expected to be significant. Example, consider a reaction where a hydrogen atom transfers between molecules. The expected rate calculated from the energy barrier does not match the experimentally observed rate, implying an additional mechanism may be at work. Analogy. This is like expecting to fill a container through a narrow pipe at a certain flow rate, determined by the pipe's size, yet the container fills much faster, suggesting that there is an alternative channel or boost that the simple theory doesn't account for. At a microscopic scale, every particle follows the laws of quantum mechanics, which allow phenomena that have no classical counterpart. Quantum tunneling, whereby particles pass through an energy barrier without possessing the necessary classical energy, is one of the prime candidates explaining these kinetic anomalies. Example, in enzyme-catalyzed reactions involving proton transfers, the protons exhibit tunneling behavior, allowing them to cross energy barriers that classical calculations would deem insurmountable. Analogy. Imagine a ball rolling towards a hill. Classical physics says the ball needs enough speed to get over the hill, yet quantum mechanics suggests the ball sometimes magically appears on the other side, bypassing the peak entirely. Several mechanisms contribute to the reaction kinetics anomalies. Beyond tunneling, the interplay of non-statistical energy distributions and dynamic recrossing phenomena can lead to rate enhancements not accounted for by classical models. Example, in gas-phase reactions, energy may preferentially localize in particular vibrational modes linked to the reaction coordinate. This targeted energy concentration can effectively lower the barrier and accelerate the reaction beyond classical expectations. Analogy. It's like having a team sport where instead of spreading energy evenly, a few players concentrate their energy on a breakthrough move, effectively outperforming a team that would share its energy equally among all players. Reactions are often more complex than a simple one-dimensional energy barrier. In many cases, the reaction coordinate involves multiple dimensions, resulting in phenomena such as multidimensional tunneling. Additionally, dynamic recrossing, where molecules cross the theoretical transition state more than once, further complicates the kinetics. Example, computational studies often reveal that when additional vibrational modes are taken into account, the effective barrier becomes smeared out, allowing for faster reaction rates through combined tunneling effects. Analogy. Think of navigating a mountain range where multiple passes, rather than a single peak, exist. Even if one pass is blocked or seems too high, the presence of alternative, lower passes can enable a quicker traversal of the range. Much like in statistical thermodynamics, where the detailed microstate information becomes practically inaccessible, the reaction kinetics anomaly also reflects an effective loss of precise control. The reaction pathway in intermediate states can involve countless micro-trajectories that, while individually reversible, collectively manifest as a rapid, non-reversible process. Example, in complex reactions, even a minute variation in the initial energy distribution among molecules can lead to dramatically different outcomes, making precise prediction from classical principles nearly impossible. Analogy. Imagine trying to reconstruct a finely woven tapestry from individual threads. Each thread's path is known in theory, but the overall pattern is so complex that restoring the original design exactly is statistically unfeasible. Understanding these kinetic anomalies has profound implications across disciplines, from catalysis and material synthesis to biological systems where enzymes operate. Recognizing and harnessing the effects of quantum tunneling and multidimensional dynamics can lead to the design of catalysts that are far more efficient than those based solely on classical predictions. Example, in the development of new catalysts, tailoring the local environment to encourage tunneling can lead to significantly improved reaction rates, impacting everything from energy storage to pharmaceutical synthesis. Analogy. It's like optimizing a racetrack for high-performance cars. By adjusting the curves and banking, even if the car's engines remain the same, the overall race time can be greatly reduced. One of the central challenges is that conventional models often assume a single, well-defined reaction coordinate. However, the reality is that even the smallest deviation in initial conditions or energy distribution can lead to a large variability in reaction outcomes, making it nearly impossible to reverse or fully control these processes on a microscopic level. Example, time reversal experiments in chemical kinetics show that even with advanced computational models, any slight perturbation in the system can prevent the reformation of the original reactant state. Analogy. This is akin to trying to unmix a thoroughly stirred cocktail. Each drop's path is well defined in an idealized model, yet in practice, reconstructing the initial configuration is effectively impossible. The study of the reaction kinetics anomaly paradox continues to push the boundaries of both theory and experiment. Emerging computational techniques, such as instant theory and ring polymer molecular dynamics, along with ultra-fast spectroscopic methods, are providing deeper insights into these non-classical pathways. Future research may lead to novel catalysts and reaction control strategies that fully leverage these quantum mechanical effects. Example, future work in nanoengineering could use precise energy localizations at the molecular scale to develop catalysts that operate at unprecedented speeds, altering the landscape of chemical synthesis. Analogy. It's like discovering a new language for nature's secrets. While the words or molecular motions are individually known, their combined grammar reveals an entirely different and more efficient way for nature to perform its literary masterpiece.